Finding Thevenin equivalent for a circuit is illustrated in this example. For steady-state AC analysis in this circuit, from perspective of this resistor load, basically from these two terminals, from this port, we want to find what is the equivalent for the whole circuit on the left side of this yellow line in the form of this, which is the Thevenin equivalent, Thevenin resistor and the Thevenin voltage. So to find that, we need to do it in two steps. In step one, what we do is we're going to open the circuit like this. So we're going to cut this wire, as if it looks like this. And what we are going to do is we are going to measure the voltage this way while the current is zero, because we cut the wires and the current I2 is now zero. So the result of that, when we measure the voltage between these two nodes, we're going to read out Vt, which in this case, because when I2 is zero, this current is shut down, nothing is flowing through 5 ohm and J6 ohm, so there's no voltage drop across these two guys. When we read V2, which is that Vt will be equal to V1, because there is nothing else, and that V1, which is the voltage across this voltage dependent voltage source, is equal to, as is defined in this problem, is equal to voltage drop across this inductor, which is J8 ohm in steady-state AC analysis. So what we need to do is we just need to write a simple KVL. Given that I2 is zero, we just need to write a simple KVL here and find I1. By finding I1, we find what voltage drop exists across this inductor, which will be V1, which is exactly the voltage drop across this voltage-dependent voltage source, which will be our Vt. So in summary, to find Vt, or Thevenin voltage, open the second loop. By second loop, I mean this loop, which means I2 becomes zero. As a result of that, when we measure the voltage like this, the Thevenin voltage, the V2 reading will be Vthevenin, which is equal to V1, which is equal to just I1 flowing through this J8 ohm. So it would be just J8 ohm times I1. So what I need to do is I need to find I1. To do that, I write a KVL here. So a KVL for loop 1. Since I2 is zero, this voltage-dependent voltage source has a zero voltage because it's completely dependent on I2. Therefore, this is effectively short. So the only thing I need to do in this KVL would be saying Vs is equal to voltage drop across these two impedances. So we would say Vs, which is 10 with angle 45. So tan 45 is equal to I1 times J8 plus 6. Great. Okay, so therefore from this, I can just conclude that I1 is equal to 10, and of course 45 degree means simply 1 plus j divided by rad 2. And here, this goes through in the denominator, it becomes 6 plus j8. Okay, so you can further simplify this by just having 10 becomes 5, 6 plus j8 becomes 3 plus j4, and then we move this to the numerator. In denominator, it becomes 25, as if you multiply both numerator and denominator with 3 minus j4. So at the end of the day, what you get is 5 divided by 25 rad 2, and you will get 1 plus j times 3 minus j4. And of course, this is in amp, because you found the current. Now, when we have this current, it's super easy because we can find just V1, as I said. We are looking for Thevenin, which is simply related to I1 like this. So as a result of what we found, we can just say Thevenin is just J8 times what you found here. It would be 1 over 5 rad 2, and then 1 plus j times 3 minus j4 just simply becomes, what you get from here is 3, and then you have minus j squared, which becomes plus, so 3 plus 4 is 7, and then you have minus j, so 7 minus j. That's what we have. And therefore, after we multiply things, finally we get to this point. We have 8 divided by 5 rad 2, and then j multiplying this will give you 1 plus 7j. And this is voltage. So we found the Thevenin voltage. Of course, you can change, and if you want, you can convert this Cartesian format of representing this complex number or phasor into a polar format. That is easy to do. So let's just move on to find the RT, which is the Thevenin resistor. For RT, we need to shut down VT, so that what we can do is a simple trick. Let me just get rid of this step here. So what I'm going to do now to find RT, I am going to, okay, so I am going to kill all the independent voltage sources. So all the independent voltage source like this one should be killed. By that I mean they should be set to 0, so they are short circuit. And as a result of that, we get rid of the impact of VT. And what we do is we apply test voltage. We test, and that test voltage would result in I test flowing through this second loop, which is the same as I2. So let's just refer to it as IT. So by IT, I mean I test. Okay, so IT or I test is flowing. And what I need to do is, so knowing that I short-circuited the independent voltage source and therefore I got rid of VT, when I apply V-test and then I somehow measure IT as a function of VT, then the only thing that I need to do to find RT is RT would be equal to, since I get rid of this guy by shorting it, the only thing that exists is RT. So as a result, RT will be equal to V-test divided by IT. So I only need to find IT as a function of V-test. That's the only thing I need to do. So going back to circuit, what is going on here? So my circuit now becomes something like this. I don't have Vs, I shorted it. I still have the two impedances here. So one inductor, which in a steady state AC analysis is just J8 ohm. And I have one resistor, which is still 6 ohm. And I have a voltage dependent voltage source, which is same as before. So it's going to be J2 I2. I2 is the same as IT, so it's going to be just J2 IT. And this circuit is done. So in this circuit, the current I1 as defined here is flowing with this direction. I'm going to write a KVL for it. In the second loop, what I have the voltage dependent voltage source, so plus minus. V1 is still the same as before, is the voltage drop across the inductor here. So I'm going to keep it, but we all know that that V1 is going to be I1 times J8. So let me just write it J8 times I1. And the same impedances I have in the second loop, so J6 ohm. And of course I have 5 ohm here in the circuit. And of course I have my V-test. And the current that is flowing here is the I-test. So with this in mind, what happens is I just need to write two KVL. So KVL for loop 1, if I write it, so KVL 1, in this case will be just the voltage drop across this guy plus this voltage should be equal to 0. So I'm going to just say It's I1 times J8 and plus 6, and then plus this J2 I test. This should be equal to 0. So that's one outcome that I have here. And of course I can divide, if my main purpose is defining I1 as a function of I test, I can also divide everything by a factor of 2. So in summary, from the loop 1 KVL, I get I1 equal to J divided by 3 plus J4 times I test. There is a negative sign into it as well, because I move this one to the other side, it becomes negative J2, but I get rid of factor of 2. So it is I test. This is the outcome from loop 1 that I wrote a KVL for. So if I do this for loop 2 and I write a KVL for that, it would be V test. So V test should be equal to the sum of all voltage drops. So V test in loop 2 is equal to I test times, when it flows to 5 ohm and J6, it causes a voltage drop. So it's going to be 5 plus J6. And then we have this voltage with this direction, it's going to be J8 I1. So it will be J8, and then it will be I1. Okay, so with this in mind, the only thing I need to do is replacing I1 with what I found here for I test. So as a result of this, V test will be equal to, let's factor out I test after I substitute for I1 from here. So it becomes I test times, of course I have 5 plus J6, and then I have J8 times this guy. J multiplying negative J becomes negative J squared, which is 1. So we get rid of that. And then we have 8 over 3 plus J4 times I test. Okay, we already factored out I test, so there is no need to rewrite I test again. That's it. So as a result of this, what I get is this outcome. So I can move I test below V test. Therefore, I can write R Thevenin equal to V test divided by I test, as we discussed before. There you go. Uh, so I divided both sides by I test, and what it remains would be just 5 plus J6, and I can move 3 plus J4 by effectively to the numerator by multiplying both the numerator and denominator with 3 minus J4. So I get 8 times 3 minus J4 divided by 25. And we're almost done. So we get effectively 8 plus 3, and then we have divide by 24. So it's roughly about 1. And we have 8 times 4 divided by 25, which is roughly about 1.24425. So we just simply simplify this, and that would be our RT. So this way you can find the RT as well, in ohm, of course. That would be the Thevenin equivalent resistor. I hope that this illustrates the general way of finding the Thevenin equivalent circuit for a steady-state circuit analysis in AC mode.